So now that we've talked about the apply-all-iter programming model, which I said was simple but had a fair amount of work stealing overhead, let's talk about a very different way to program the functions that we're doing here. And this is what I call applyAllSplit. And this particular method uses recursive decomposition to disperse tasks to worker threads. And one of the consequences of this approach is it's going to have less work stealing for reasons you'll see in a second. Again, the basic behavior is the same parameters are passed in, and the parameters are the list, the op, and the fork join pool. But the design is completely different than what we saw before. And in particular, it defines this nested class called splitter task that will be used to recursively partition the list evenly and then run each half in a fork join task. And it does this recursively. So it's going to be dividing the list up into smaller and smaller chunks until, of course, it bottoms out, because you can only divide things in half so long before you run into the end, basically log n times. And the way it's going to do that, it's going to define a splitter task that extends recursive task. And this use case is sort of the reason why the fork join framework exists, to be able to do this splitting evenly and efficiently. What it's going to do is it's going to start out by creating a splitter task, this guy, an instance of splitter task, for the entire list. And then it's going to wait for the result. So it's going to call the fork join pool invoke method, which, as we all know, is the way you get non-fork join clients into the fork join pool, blah, blah, blah. And it's going to call that and pass that in. Let's take a look at how the splitter task is implemented. It's really quite interesting. You can see the splitter task is going to have its own little field, which is a list. And this list will always store half of the elements that were passed to it. So you'll see how that works in a second. So what's going to happen here is we're going to be passed a list. We'll start out with the entire list at the beginning. And then we're going to have the compute method. So the constructor takes whatever parameter is passed. In this case, it was passed the entire list to start out with. So it takes the list, it stashes it away in this field. Remember, that's just a reference, so it's not copying anything. So it's going to store that reference there. Here's the compute method. And what this does is it's going to recursively perform computations in parallel on a subset of the list, in particular, half of the list. Let's take a look and see how this works. So if the size of the list at this point is 1 or less, it should be 1, but let's say it's 1, then we've reached the base case of the recursion. So as you can see here, what we're going to do is we're going to make ourselves a new array list here, which will have ultimately 1 item. And then we go ahead and we say for each element in the list, there should be 1 item only. We're going to go ahead and apply the function passing in type T, element T of type T, and we're going to add that to the result list up here. So that's going to be added there. So that's the base case of the recursion. And then we're just going to return the list, which will have the results of applying the function to 1 element. That's the base case. Now let's take a look and see what happens if we have a list that's bigger than 1. So what we're going to do in that case is we're going to recursively and evenly partition the list, kind of like taking a candy bar and breaking it in half evenly and then sharing it. So what we're going to do is we're going to take the size of the list divided by 2. That's the midpoint. Then we're going to go ahead and make ourselves a new fork join task, which will be a list that will contain half of the elements. And the sublist we're going to create is going to be from 0 up to, but not including the midpoint. And we're going to make a new splitter task that covers that half of the list. And then we're going to fork that, which stores it in a fork join task. Remember, fork doesn't actually cause things to run. It just arranges to run it by putting it into the deck of the calling thread. And then what happens here, if you think about this, is that larger partitions are pushed onto the deck before the smaller ones, which helps with the work stealing, because you're always stealing bigger things, which is what you want. We then go ahead and make another list. Actually, what we do is we reinitialize mlist to be the current mlist from mid to the end of the list. So we take the right half. So up here, we did the left half of the list and make that a new thing. We call that LT for left task. And then we go ahead and we update the current mlist with the right half of the list. So again, keep the candy bar metaphor in mind. Here's the left-hand part of the candy bar, and here's the right-hand part of the candy bar. So now we've got mlist updated. And then we turn around and we recursively call compute, which is calling this function again, except now we've updated mlist to only be the right-hand part. And in the meantime, the fork that we did back here will have started running in some thread. Maybe it's been stolen. We don't know. It's probably going to be stolen, honestly, because we're going to be calling compute here. And then when compute finishes, we come back and we call LT for left task join. So compute gives us the right result, which is the list of results, which is the right-hand side. The LT.join call, which remember does not physically block, but logically blocks because it can still do some processing. You get back the left result, which is the left-hand side of the candy bar. And then what we do, don't you love my animation here? We take the two pieces and we put them back together again. And we then go ahead and take left result and we add the right result to it. And then we return the left result. So what we're doing basically is we're running these two things in parallel. And then we're waiting till they're done. And then we connect them by adding the right-hand side to the left-hand side and returning the left-hand side, which now contains everything. Now, the thing to remember here is data will be copied since these lists are implemented via array lists. So we're making a copy of the data. So there's some copying going on. Remember, there was really no copying going on in the earlier solution that we had, but there is now going to be some copying going on. So that's going to be a little bit higher overhead. This implementation is arguably a little bit harder to understand, a little harder to program than the original one, since it's recursive. Now, once you understand the concept of breaking things in half, it's not that hard. But when you're first confronted with it, you're like, oh gosh, I got to make sure I get the sizes right. I've got this recursion with a base case up here that I have to deal with. So the code is arguably longer and more complicated. But we'll see that there's a benefit to that. By the way, I should also mention here something very important. Compute needs to be called before join. And that's because join will logically block, and we don't want that to happen. We want compute to be running in parallel with the left-hand side that we've forked over here. Okay, so now let's go ahead and visualize this technique and see what it looks like. So as with before, this code is what we do to get the non-fork join task client to insert a task into the fork join pool, which you can see we do by calling invoke, making a new splitter task that covers the whole list initially. And then at that point, things are very different from what we saw before. So what we do now is the compute method, as we saw, will be splitting stuff up into chunks, and it's going to end up recursively decomposing this stuff into worker threads in the fork join pool. And as a consequence, the work stealing overhead is going to be lower because we're distributing these calls amongst different threads in the fork join pool. However, there's more method calls because we're doing this recursively, and there's also more data copying because we have to make these sublists and so on. So it's going to be a little bit more expensive from a data copying and method call point of view, but there's going to be less work stealing overhead. So we'll see how that all pans out when we look at the performance results. As you can see here, this is something also very important to understand. We're forking and then we're computing. And compute is actually borrowing the thread of control of its parent. We could have forked the right-hand side too, but that's overkill and it's really not getting you anything. So we're going to borrow the thread of the parent to compute the right-hand side, but we're going to fork the left-hand side. And that's just a common idiom you see all the time with a fork join pool. What we end up basically here is a balanced tree of join calls, which is going to scale up better than apply all iter, where there was just one thread that was waiting for everything to finish. Okay, so that's the end of the applyAllSplit model, which is a bit more complicated, but we'll see later that in some circumstances there's a win doing it that way.